So we're very happy to have Tristan Collins, who will be telling us about SYZ mirror symmetry for the Pezzo surfaces and rational elliptic surfaces. Okay.
Thanks a lot, and thanks a lot for the invitation to speak. So I am going to talk about some joint work with Adam Jacob and Yu-Shen Lin, and I should say that my perspective, or at least my approach to this kind of stuff, is much more differential geometric and geometric analysis based. So that is where I'm coming from. All right, so let me tell you about what I'm going to try to say in this talk. So I'm going to begin by just recalling the main players in this talk, which are del Pezzo surfaces and rational elliptic surfaces. So I'll just try to recall what those are. And then I want to explain Denis' picture of mirror symmetry for divisor complements. And then I want to talk about some work from last year on SYZ fibrations of del Pezzo pairs and some applications. And then I'll start talking about newer work, which is focused on the other side of this correspondence, which is rational elliptic surfaces with an IK singular fiber. And in particular, I want to talk about SYZ fibrations, and then mirror symmetry for these two classes of objects, and some sort of differential geometric interpretation of mirror symmetry for Hodge numbers. Okay. So let me just recall, so a projective surface is del Pezzo if it has ample anti-canonical bundle. So we write that as minus ky being positive. So these are all classified. They're either, that should be P1 cross P1, not P1 cross P2. P1 cross P1 or obtained by blowing up P2 at between 0 and 8 generic points. In this case, each of these del Pezzo surfaces has degree k, which is 9 minus the number of points that you've blown up. And if you look at degree 8, then of course you have also the P1 cross P1 family. So for degree not equal to 8, there's only one deformation family of all of these del Pezzo surfaces. So they're just classified by blowing up. And then for k equals 8, there's two families, which are given by the blow up of P2 at a point and P1 cross P1. So an easy fact is that these all admit a smooth divisor in the anti-canonical linear system, which is something that I'm going to use repeatedly throughout the talk. Okay, so those are del Pezzo surfaces. So they're fairly simple. You just take P2 and blow it up at some points, or P1 cross P1. The other players are rational elliptic surfaces, which are maybe slightly less common, although I assume in this audience they're well known. So a rational elliptic surface is a surface admitting a relatively minimal elliptic fibration onto P1, which has a global holomorphic section. So maybe a nicer way to think about these surfaces is that you take P2 and you take two cubics, which are sections of the anti-canonical bundle, and you blow it up at the intersection of those two smooth cubics. So then it's an easy calculation that for these surfaces, the anti-canonical bundle is effective. They have a nice fibration to P1, which is just given by sections of the anti-canonical bundle. And the fibers of that are exactly linear, are elements of the anti-canonical linear system. So in this case, Kodaira classified all the possible singular fibers that can occur, not just for rational elliptic surfaces, but for elliptic fibrations. And we're going to be really focused on rational elliptic surfaces that have a singular fiber of type IK. So an IK singular fiber, so if k is not 1 or 2, then this just corresponds to a wheel of rational curves with -2 self-intersection. It's a nodal curve if k equals 1 and a smooth fiber if k equals 0. So let me just draw a picture of these. We'll see how well this works. So if k equals 1 or k equals 0, then we just have a smooth elliptic fiber. If k equals 1, Then we have a pinched torus, so a nodal Lagrangian or nodal sphere, nodal holomorphic sphere. And if k equals 2, or bigger than or equal to 2, then we just have a bunch of these guys which intersect each other. So you can imagine that this is obtained by degenerating a smooth torus fiber and pinching k loops, or k minus 1 loops, or whatever the right number is, k loops, I guess. Okay, so these are really going to be the other cast of characters in this talk. So in both of these cases, you have this nice anti-canonical divisor. So you can take an element of the anti-canonical linear system, and then there's a section of the anti-canonical bundle which cuts out this divisor. So in other words, this section vanishes only on the divisor. But then the idea is that, well, then you can invert this section at least away from this divisor, and you'll get a holomorphic 2 form on the complement of the divisor, which has a simple pole on D. So in particular, that makes these divisor complements in rational elliptic surfaces or del Pezzo surfaces, or of course more generally, right? I mean, this construction makes sense anytime you have effective anti-canonical bundle. That makes the complement of this divisor a natural non-compact Calabi-Yau manifold. So in this case, when I say Calabi-Yau, I really mean just that it has a holomorphic 2-0 form, or N0 form, if you like, in higher dimensions. I don't mean Calabi-Yau in the sense that there's a Ricci flat Kähler metric, because Yau's theorem obviously doesn't apply in this case because these divisor complements are non-compact. So I want to recall some of the, well, I mean, this is well known to everybody, but let me recall it for completeness, some of the elements of SYZ mirror symmetry. So if you have a Calabi-Yau manifold with a holomorphic volume form, then we can talk about special Lagrangians. So special Lagrangians are Lagrangian, so they annihilate the symplectic form. That should be the Calabi-Yau symplectic form. And after possibly rotating the holomorphic top form by a unit complex number, a constant unit complex number, these Lagrangians are calibrated by the holomorphic volume form. So the reason that these were originally introduced, of course, is that they're automatically volume minimizing in their homology class. So that just follows from being calibrated. That was the perspective that Harvey and Lawson took when they were originally studying these things. But it turned out after the fact that they turned out to be very important in mirror symmetry, as we now know. And it's important to note that this, of course, this definition also makes sense if we don't assume that the symplectic form is the Calabi-Yau symplectic form. But in that case, the sort of differential geometric application of these manifolds, which is that they're volume minimizing, is no longer true, because there's no connection between the symplectic form and the Riemannian metric and the holomorphic volume form. Okay, so this sort of this minimality depends crucially on them being on the symplectic form being Calabi-Yau. So the SYZ conjecture, and I'm going to state this somewhat vaguely, but it predicts that at least maybe near a large complex structure limit, as appeared in Yang's talk, that this Calabi-Yau manifold should emit a special Lagrangian torus vibration onto some base B. And then Hitchin explained how the base of this vibration inherits two different affine structures, which come from the symplectic structure and the complex structure. And then mirror symmetry is supposed to be obtained by this T-duality construction along the fibers. You take a torus and you replace it with its dual torus over the same point in the base. And then that's supposed to be compactified to the mirror Calabi-Yau. The dual manifold also admits this special Lagrangian torus vibration. So it has these dual torus fibers. And so in particular, the base again inherits a complex and symplectic affine structure from this dual vibration. And then mirror symmetry is supposed to exchange these two. So it's supposed to exchange complex affine structure with the symplectic affine structure on the mirror, and vice versa. Okay, so that's That's the sort of rough statement of the SYZ conjecture. Of course, probably false in this generality, or this, but there are some versions of this which you can weaken various parts, etc. So anyways, this is what I'm going to take to be the SYZ conjecture. Okay, so what about mirror symmetry beyond Calabi-Yau? So of course, to talk about the SYZ conjecture, we needed to have this Calabi-Yau structure. So what about for non-Calabi-Yau manifolds? So of course, this is well studied, and there's been a lot of talks about it in this very workshop. But the picture is that if you have a non-compact, or if you have a manifold which is not Calabi-Yau, so for example, if the anti-canonical bundle is effective, then the expectation is that the mirror should be a Landau-Ginzburg model, or perhaps a partial compactification of a Landau-Ginzburg model, which is some non-compact Kähler manifold with a holomorphic function from M to C. Now, what do I mean by a partial compactification? I mean, you can view this map from M to C as some sort of fibration. So the preimage of a point in C is some holomorphic submanifold of M, and then you can try to compactify those fibers to get a bigger manifold M bar that has a fibration over C. Okay, so that's the general picture. So Denis laid out a sort of general picture for how to construct these mirror manifolds to Kähler manifolds with effective anti-canonical bundles by applying this sort of SYZ philosophy to the complement of an anti-canonical divisor. So in other words, if you, as we discussed before, if you have a compact Kähler manifold with an anti-canonical divisor, you can look at the complement as a non-compact Calabi-Yau, and then you could ask whether that non-compact Calabi-Yau manifold has an SYZ fibration, and then you could try to apply T-duality to that non-compact SYZ fibration and construct a mirror. So that's what I want to try to carry out in this talk for the examples of rational elliptic surfaces and del Pezzo surfaces. So mirror symmetry between these two characters, del Pezzo surfaces of degree K and rational elliptic surfaces with an IK fiber, is actually very well studied. I mean, it's been mentioned a lot already in this workshop. Primarily at the algebraic and homological levels. So just to mention the sort of very incomplete list of results, but Aru, Katsarkov, Orlov proved one direction of homological mirror symmetry. So they showed that they could show that the B model on the del Pezzo surface is the same as the A model on the rational elliptic surface. And this was recently generalized by Hacking and Keating. Gross-Hacking-Kiel, of course, constructed synthetic mirrors along the lines of the Gross-Siebert program. And then there's some work on the sort of on mirror symmetry at the level of Hodge numbers by Luntz and Przylkowski. And this is a little bit non-trivial because these non-compact Calabi-Yau manifolds don't really have obviously well-defined Hodge numbers. And so Katsarkov, Kontsevich, Pantev made a sort of proposal for how one should define Hodge numbers, and Luntz and Przylkowski computed that for these examples you do get mirror symmetry for Hodge numbers. Well, at least I think technically KKP proposed 3 definitions of Hodge numbers, and Luntz and Przylkowski showed that 2 of them were exchanged and one was not. So they so there's some notion of mirror symmetry for Hodge numbers on these manifolds, but it's kind of complicated. Okay, and then there's also work of Doran Thompson, who studied this del Pezzo rational elliptic surface mirror symmetry at a lattice theoretic level. Okay, so what do I want to do? I want to take the more classical SYZ point of view. Being a differential geometry, this is the kind of thing that appeals to me. So I want to explain a proof of SYZ mirror symmetry for del Pezzo surfaces of degree K and rational elliptic surfaces with an IK fiber. And I want to compare what we find with the other approaches that most notably the Gross-Hacking-Kiel work. I want to explain a differential geometric approach to defining the Hodge numbers in terms of moduli of complete Calabi-Yau metrics. And then along the way, there will be some applications to existence of some sort of newish Calabi-Yau metrics, a question of Yau, and various other things which just sort of happen to pop out along the way. So the first thing that I need to tell you, also you should just stop me when we should break for questions, and have this talk gets gradually more formal as we go along. There's no obvious cutoff point. So let me maybe first tell you if I want to talk about SYZ mirror symmetry, then I need to talk about Calabi-Yau metrics. So I need to tell you that these exist and what they are supposed to look like, or what they do look like. So the first ingredient, so on the Del Pezzo side, is a theorem of Tian and Yau, which says that if you have a Del Pezzo surface with a smooth anticanonical divisor, which isn't necessarily an elliptic curve by adjunction, and a holomorphic volume form with a simple pole on D, then there exists a DD bar exact complete Calabi-Yau metric, which I'll call the Tian-Yau metric on the complement of D, which satisfies the Monge-Ampere equation. So I've scaled things appropriately here, but I mean, the point is it satisfies the Monge-Ampere equation. And what's really crucial is that, so the way this is constructed, of course, in the non-compact case, the best hope you have is to have some model for what your solution to the Monge-Ampere equation should look like at infinity, and then try to produce a Calabi-Yau metric which is asymptotic to that model. So here there is a model, it's called the Calabi model. And I'll tell you what it is because it's going to play an important role. And they have they have good estimates for how these metrics are supposed to converge to this model geometry at infinity. So, and it's worth remarking that there's no reason to restrict to surfaces here. This Tian-Yau theorem holds in all dimensions, but I'm only going to use it on Del Pezzo surfaces for now. So let me not state it in its full generality. Okay, so what is the Calabi model? So the Calabi model is supposed to model the geometry of the elliptic curve inside of a Del Pezzo surface. So you can imagine that we're really just trying to write down some Calabi-Yau structure on the normal bundle of an ample divisor. So, okay, we take an elliptic curve D with a holomorphic volume form omega D, and take E over D to be an ample line bundle. And then we take the Calabi-Yau metric on D that's in the first Turing class of E. So this is just a flat Kähler metric. And now we consider the punctured unit disk bundle over this Calabi-Yau, over this elliptic curve. And we take a holomorphic volume form on this total space, which has a simple pole on the 0 section. And then we write down this metric. So this was, I think, this was originally constructed by Calabi. So you take DD bar of the log of the norm of a section squared with respect to the Calabi-Yau metric on E, and you raise it to this funny power of 3/2. So you can check that that's a Kähler metric, and that it's complete at the 0 section. So it's of course incomplete at 1, but that's supposed to be sort of in the interior of the manifold anyways, that we're going to study in the end, but it's complete at the 0 section. And it satisfies the Monge-Ampere equation with this volume form up to choosing the appropriate constant, normalizing constants. Okay, so that's the model geometry. So how should you visualize this? Well, the best way to visualize this is to think of this manifold, this total space of L, as being fibered by the circles in the disk bundle. And then you can compute what the metric is, and what's happening is that as these circles get smaller, so they go towards the 0 section, they always have the same volume, but they collapse, so the circles get smaller, but the circle bundles get longer, so that the volume's always constant. One key observation for us is that if you look and you take a special Lagrangian in the elliptic curve, And you just take a circle over that special Lagrangian. So you take the circle bundle, the like natural circle bundle of radius epsilon in the total space. Then that is special Lagrangian with respect to this Calabi model, Calabi-Yau structure. And it's topologically a trivial bundle because L is slag. So it's L cross S1. And they all have the same volume. So independent of epsilon, again, they all have the same volume. So let me try to draw a picture of how to think about this. So again, the picture is going to be, so I'm going to draw an elliptic curve as a line. So here's my elliptic curve D. And over this elliptic curve, I have a disk bundle, but this disk bundle is foliated by circles. So here's maybe a large value of epsilon. And as epsilon gets smaller, so as I go closer and closer to the zero section, these disk bundles get thinner and longer. So they get they all have the same volume. So they get infinitely long and infinitely thin as epsilon goes to zero. And then a special Lagrangian, well, in this picture, a special Lagrangian is just going to be a point in D. And so I get a special Lagrangian over this, this point by just taking the circle bundle. So this would be a special Lagrangian in this model geometry. Okay, so that's the Calabi model. So using this, we proved, so paper from last year, we proved that in this situation, if you have a del Pezzo surface with a smooth elliptic curve, and you look at the complement of this elliptic curve and equip it with the Tian-Yau Calabi-Yau structure, then there's a special Lagrangian fibration on this space with base being R2. And in fact, you get infinitely many such distinct special Lagrangian fibrations, because each special Lagrangian fibration essentially amounts to a choice of a closed loop in D. So for every homologically distinct closed loop, you'll get a distinct special Lagrangian fibration. So I think the next thing I'm going to do is try to describe the proof. So maybe now if there are any questions about the Calabi model or del Pezzo surfaces or anything, now is a good time to. Yes. Okay. If there are no questions, I'll try to describe the proof. So the proof goes in the following way. So you fix a closed geodesic in D, and then you can translate that geodesic around, and you get a special Lagrangian fibration of the Calabi model. Right. So in our picture, you just take you translate your closed loop around, and over each point you take circles of varying radii, and these will fiber the whole Calabi model. Okay, so that's how you get a special Lagrangian fibration of the model space. So now, oh, there's a spelling mistake. So we can transplant this into the Tian-Yau space and get not a special Lagrangian fibration, but just a Lagrangian fibration in a neighborhood of infinity. So we take this model picture and we transplant it into the actual Tian-Yau space, which looks maybe something like this. And you have all these tori, which are Lagrangian, but not special Lagrangian. They're sort of approximately special Lagrangian, something like this. Okay, so this is like a model SYZ fibration, which is transplanted. Okay, so then the idea is to try to correct this model SYZ fibration to a genuine SYZ fibration. And the first thing you need to do is you need to understand how quickly the Tian-Yau metric converges to the model geometry. So once we understand that, which we do thanks to work of Tian-Yau and Hein and others, we get good control of the geometry. Now, of course, as you go further out in the manifold, as we said, these cylinders are getting very, very small and very, very long. So the geometry is degenerating in a sense. So they're collapsing circle bundles with fixed volume and unbounded diameter. But the rate at which the geometry degenerates is polynomial in the distance from a fixed point. So the geometry degenerates like a polynomial. I mean, you could make that precise, but let's just take that as a slogan. While the mean curvature decays exponentially. So in particular, as you go further out, the geometry gets worse in a polynomial way, but you get closer and closer to a minimal surface exponentially fast. And that's good enough to run the Lagrangian mean curvature flow. So we can run the Lagrangian mean curvature flow and show that the sort of, that the smallness of the mean curvature is enough to control the degeneration of the geometry, and prove that as long as you start outside a large compact set, the Lagrangian mean curvature flow will always converge smoothly to a special Lagrangian in the limit. And in fact, we can show that actually the Lagrangian mean curvature flow deforms the whole fibration to a limiting fibration. And really the only thing you need to show there is that if you start with disjoint Lagrangians at the initial time, then they have to flow to disjoint special Lagrangians in the limit, and that's Floer theory is well adapted for that kind of argument. So this gives us like a sort of homotopy from the model Lagrangian fibration to the actual special Lagrangian fibration near infinity.
Can I ask a question?
Yes.
Well, you said Floer theory, right?
Yep, I did say Floer theory.
I listened to a previous talk, I think it was you, about your work, but I couldn't come to a conclusion whether I can use this Tian-Yau metric to do Floer theory, in the sense that is it geometrically bounded, or it seemed to me like it wasn't. But since you used Floer theory, you probably thought about this.
Well, we just need to define the Floer theory between two Lagrangian fibers.
But still, you need to get like C0 bounds, right? Because it's non-compact, so you need Gromov compactness.
Oh, so that we can do. Yeah, we can do Gromov compactness, and yes, so that we can do. Because actually, so the Tian-Yau metric decays and sort of the geometry degenerates sufficiently slowly that you can still do Gromov compactness. So that actually will appear later in the talk. Yeah.
Okay, thank you.
Yeah. Yeah, that's a slightly subtle issue, but yeah, it turns out that you can still do the Gromov compactness. Okay, so now at this point, the main issue, so at this point we have a sort of model, we have a special Lagrangian fibration in a neighborhood of infinity, but of course I claimed that there was a global SYZ fibration, so now I need to explain how to extend this vibration from a neighborhood of infinity into the interior of the manifold. So that's done by using a hyperkähler rotation trick. So this is, at this point, up until this point, essentially everything except for the Floer theory part works in arbitrary dimension, assuming you have some sort of special Lagrangian to begin with. So now we really start to use the properties of surfaces. So by a hyperkähler rotation trick, you can make these special Lagrangian tori become holomorphic curves. And then by the MacLane deformation theory, if you have a smooth fiber in a smooth special Lagrangian torus fiber in your manifold, it sweeps out a local fibration. So the only issue is to try to figure out what happens if there are singular fibers. But as Umit pointed out, this is where we can use the theory of J holomorphic curves, Gromov compactness, in this whole package, which we can suitably generalize to this setting. And it allows you to take limits of smooth curves. So you start with some smooth fiber, you deform it, it sweeps out a local fibration, and then if this fibration breaks at some point, you can take a limit of those smooth fibers and get some sort of singular fiber. So we can classify, so you can classify all possible singular fibers, and this is basically just Kodaira's work of classifying singularities of elliptic fibrations. And then using arguments from the theory of J holomorphic curves, particularly deformation and moduli theory, together with intersection theory, you can show that in any compact set, there can only be finitely many singular holomorphic curves, which are obtained as limits of smooth fibers. So from this, you can easily show that there's a global fibration. So let me just draw the picture. So we have, all right, well, here's our picture. So, okay, let me draw a new Tian-Yau manifold. So we have our Tian-Yau manifold, something like this. We have a nice special Lagrangian fibration out here. So let me draw the special Lagrangians as points. Yep. Now, if I have a smooth fiber, it deforms to give me a fibration in a family. So suppose that there was some point here through which there was no special Lagrangian torus, singular or smooth special Lagrangian torus fiber, which was homologous to our smooth fiber. So then you just consider like all possible paths that connect your given point to your target point. And by deformation theory, we know that the set of points on this curve which admit smooth special Lagrangian fibers is open. And then by compactness, we know that if the curve, if you can't have a smooth fiber all the way up to the end point, then you get a singular fiber on that curve at some point. But if you just move that curve around, since you know that there are only finitely many or countably many singular fibers, you can of course find some curve which avoids all of them. And then that tells you that this smooth fiber deforms all the way up, possibly to the limit. At the limit, you could of course get a singular fiber. So that's kind of the argument. Okay, so all of this works very generally. It doesn't really depend on Del Pezzo surface at all. It depends very much on the geometry of the Tian-Yau metric, but not so much on the it depends on the sort of rough geometric properties, like the decay of the Riemann curvature, the decay of the injectivity radius, all of this kind of stuff. But it doesn't depend on exactly knowing the Calabi model or anything like that.
So Tristan,
okay, so maybe yes.
Stopping point.
Yeah, sure. This is a good stopping point. Yep.
You have questions? Anyone?
What can you say about the geometry of the hyperkähler rotation? I mean, we're starting with something algebraic, but there's no guarantee that the hyperkähler rotation thing is algebraic.
Right. Yeah. So that's a great question. So that's, I think, the next slide even.
You don't have to do the next part of the talk.
So yes, we can say quite a lot. And what we can say is that the hyperkähler rotation, you can always compactify it to a rational elliptic surface by adding an IK fiber. Yeah.
And where K is the degree of the Del Pezzo.
Is the degree of the Del Pezzo, yeah. Yeah, exactly. Yeah.
So it's maybe kind of more analytic question. So when you run this kind of Lagrangian mean curvature flow, so do you have any kind of finite time singularities? Because I mean, in the end, you want to get singular fibers as well, right?
Right. So
disappear at infinite time or something.
So because, well, what happens is that because you're far out at infinity, this is almost like a small perturbations result. I mean, or like local stability for Lagrangian mean curvature flow. You're basically starting in starting very close to a special Lagrangian because the mean curvature is so small. So actually, just from smoothing estimates for the flow, you can rule out finite time or infinite time singularities. So basically, you know that in the end, you should only get finitely many singular fibers, right? For like topological reasons. And so all those singular fibers they don't, if you go far outside a big enough compact set, you don't see any singularities.
Okay. What I mean is inside a compact set.
Oh, so inside a compact set, we don't have initial data even to start the flow with. We don't even know that there's a Lagrangian, I guess. Well, I guess maybe you could produce one, but yeah, so we really only use the Lagrangian mean curvature flow like really close to infinity. And then inside the manifold, you see the singular fibers only as limits of J holomorphic curves, essentially.
Right. So the way you somehow get the Lagrangian, special Lagrangian fibration in the interior region is by this deformation argument after you have done all the flow things. Is that correct?
Exactly. Yeah. Exactly. Yeah.
Okay. But why do you choose to do this flow strategy rather than doing the perturbation argument in some purely elliptic framework?
Yeah, so I had a feeling that you might ask that question. I mean, there's I think the deformation theory, because the geometry of these special Lagrangians is degenerating at infinity, you really need to have some quantitative idea of how fast the improvement in the mean curvature beats the degeneration of the geometry, and that just seemed easiest to me to obtain from the flow. Also, I think this result of saying that the flow actually flows the whole special Lagrangian fibration to the limit is, well, we need that later on to justify the compactification as a rational elliptic surface. And I guess you could get that also from a perturbation argument by arguing that the perturbation depends smoothly on the local data, but in the end, it seemed like conservation of difficulty to do it one way or the other. So. And I like flows. So.
Okay.
Yeah, it's a good question though.
But you have to also develop this kind of Gromov compactness in this degenerative setting. I mean, once you use this flow strategy, I presume if you do a kind of perturbation strategy with sufficiently good implicit function theorems, you might not necessarily have to. I mean, the kind of disjoint property, if you know everything's a small perturbation, you might get it without doing any flow theory.
Right, but we need without doing any Floer theory. I'm not sure if you could do it without Floer theory, because you could still have this situation where you have very, very close Lagrangian initial data, which you then somehow is perturbed to the same special Lagrangian in the after. I mean, it could conceivably happen, right?
Right. But I mean, so I guess, I mean, if you know somehow that after perturbation, you're not just C0 close, but actually C1 close. I mean, the tangent planes are not tilted too much. Then the kind of, at least at infinitesimal level, you would think that disjointness is actually also preserved.
Yeah, right. Yes. Yeah, you would. Yep.
I mean, my personal feeling is that maybe that strategy actually could save you some work. I mean, if you had seriously tried that, but I mean, it's your taste, so.
Yeah. Yeah. Well, you know, at MIT, there's a lot of mean curvature flow, so somehow it's in the air.
Well, maybe you want to practice with the flow in order to tackle Joyce's conjecture, I suppose.
Is it possible to replace the smooth curve at infinity with maybe a simple normal crossing divisor?
So that's an excellent question. In that case, it's not known what the Calabi-Yau, if there exists a Calabi-Yau metric. At least not in the case of del Pezzo surfaces with a singular anti-canonical divisor. So the answer is ideally yes, but we don't know. We don't even know what the Calabi-Yau metric is.
I see. Thank you.
Yeah. Sorry.
Other questions? Maybe I'll pause the recording for a second.
Okay, so let me start the second half by answering Mark's question right away, which is, so if you take a del Pezzo surface of degree k and you take this SYZ fibration, any of the SYZ fibrations you choose, then you can hypercalar, so like discussed, you can hypercalar rotate, so this SYZ fibration becomes a holomorphic torus fibration over C, and then you can prove that that there is a rational elliptic surface which compactifies this fibration with an IK fiber over infinity, so that this SYZ fibration is the restriction to the complement or this SYZ fibration is the restriction of the holomorphic torus fibration to the complement of the IK singular fiber. So so that describes the fibration, at least some sense that it describes the fibration pretty well. And so let me just point out that there's a question which Yau apparently asked in the 80s, which says, which was to understand what the symplectic form of the hyperkähler rotated Tian-Yau metric is. So you start with this Tian-Yau metric has a Ricci flat Riemannian Kähler metric. This hyperkähler rotation changes the complex structure, so it fixes the metric. So you get a new symplectic form on the rational elliptic surface, which is again the symplectic form of a Ricci flat Kähler metric. So Yau wanted to know what that symplectic form was. So I'll try to describe and answer that question later, which probably not surprising to some of you. So a few remarks, which is, I said already, this Lagrangian mean curvature flow part of the argument works well in any dimension, and it allows you to lift special Lagrangians in the Calabi-Yau at infinity to special Lagrangians in the interior of the manifold. Of course, in dimensions, higher dimensions, you need to assume that there's a special Lagrangian to begin with. But of course, thanks to Yang's talk, we now know that their special Lagrangians are maybe not as hard to find as we used to think. We also prove analogous results for rational elliptic surfaces with where you take D to just be a smooth fiber. So I won't go into that since it's not really important for this talk, but this can be done. And then for some cases, we can identify all the singular fibers of this SYZ fibration. So for example, if you take P2, then we know that you get 3 nodal spheres as the singular fibers. And if you take a generic rational elliptic surface, then you get 11 or whatever the appropriate number of, or 12 nodal spheres in the interior. So those 2 results were expected by Denis. So confirm that. So now let me talk about the newer results, which are focused on the rational elliptic side of the story. So ideally, we'd like to prove similar results for a rational elliptic surface with an IK singular fiber. So I'd like to discuss that, but the first thing I need to do is tell you what the Calabi-Yau metrics are supposed to look like. So there's near an IK fiber, so any elliptic fibration over a disk with an IK fiber over 0 is always biholomorphic to this model fibration. So you take the disk delta star, and you look at Z in the disk, and you just quotient C by the lattice Z mod plus Z plus K over 2 pi squared and minus 1 log Z. So that gives you a holomorphically varying lattice on the punctured disk, and you can take the quotient of C by that lattice. So this is the model fibration for an elliptic fibration with an IK singular fiber, and it can be completed over 0 to give you an IK singular fiber. So the holomorphic volume form is always of this form kappa of Z dx wedge dz over Z. Well, for us, when we assume that there's a simple pole on the fiber, kappa of Z is some holomorphic function, which is not 0 at 0. So I'm going to assume for simplicity in this talk that kappa is always 1. That's not the case generally, but dealing with the case of kappa not being 1 is a sort of minor complication. Okay, so we have this model geometry. So how does this biholomorphism, so if you have any elliptic fibration over a disk, and assume it has a local section over the punctured disk, then you get a map to this model geometry by just using the fiber-wise Abel-Jacobi map for a suitable choice of basis of the first homology of the fiber. So that's how you identify an elliptic fibration with this model fibration. And then Green, Shapir, Vafa, Yau wrote down a flat Calabi-Yau metric on this model space, which is flat along the fibers. So it's called a semi-flat metric. It has the following forms. It looks very complicated, but you don't need to understand. I mean, the formula is not so important. I just wanted to write it down. There's a parameter here. You'll see epsilon, which is the volume of the fibers of the fibration. And the only important thing that you need to observe here Okay, well, let me say one more thing, which is that a semi-flat metric with respect to a section is then the pullback of this model semi-flat metric by this relative Abel-Jacobi map. So we're going to call that a standard semi-flat metric with respect to sigma. So there's a choice of section that goes into this model is the thing that I wanted to emphasize here. And the other thing to observe is that there's actually a special Lagrangian fibration of this model geometry as well, where you just take the imaginary part of x equals constant slices in the fiber, cross a circle in the base of any radius. So this gives, you can check again using the formula that this gives a special Lagrangian fibration. Okay, so here's the existence theorem, which is a theorem of this Heinz thesis. It says if you have a rational elliptic surface with an IK fiber over infinity, and we take the homology class of this bad cycle, then if you give me a Kähler form on the complement of this IK fiber, which pairs to 0 with this bad cycle. So notice that that's going to be essential. I mean, that's a cohomological condition. If you want to have a Calabi-Yau metric, which is asymptotic to this semi-flat model, it has to pair to 0 with this bad cycle, since the bad cycle is Lagrangian, right? And then there's also this condition that the initial Kähler data has a finite volume. Then for appropriately chosen constants, you can produce a Calabi-Yau metric asymptotic to this semi-flat metric. So there's a few points here that I want to emphasize, which is this condition of pairing to 0 with this bad cycle. So that's one point that's worth emphasizing. This condition about having finite volume for your starting metric that you plug into this ansatz. And then the theorem says that there is some section such that you get a Calabi-Yau metric asymptotic to the semi-flat metric with this, with respect to this section, after possibly rescaling by a suitably large constant. And again, Hein has very precise estimates for how this Calabi-Yau metric converges. So the main problem on this rational elliptic surface side is that if you want to understand the Kähler moduli, so for example, to do mirror symmetry or to define Hodge numbers, etc., then you at the very least need some parameter space to parameterize Calabi-Yau metrics. So there's no obvious, I mean, from this theorem, there's no obvious parameter space. So let me try to explain why. So the first thing is to observe that the de Rham cohomology, second de Rham cohomology of the complement of this IK fiber has dimension 11 minus K, while this condition of pairing to 0 with the bad cycle cuts out a 10 minus K dimensional hyperplane. So it's natural to ask whether there are Calabi-Yau metrics in the remaining dimension worth of de Rham classes, at least the ones containing Kähler representatives. The second thing is that Hein's theorem tells you that there's a Calabi-Yau metric in the Bott-Chern cohomology class of your initial Kähler metric. So this Bott-Chern cohomology is a refinement of de Rham cohomology. But Hein's theorem leaves open the possibility that you could have even distinct Calabi-Yau metrics in a fixed Bott-Chern class. So even the Bott-Chern cohomology is not a great parameter space at the moment for parameterizing Calabi-Yau metrics. The next thing is that the Bott-Chern cohomology is actually not a great parameter space anyways, because it's isomorphic to the second de Rham cohomology across the space of holomorphic functions on C. So it's sort of wildly infinite dimensional. So it's not, so if you wanted, for example, to define Hodge numbers in terms of Bott-Chern cohomology, which is what you would do in the case of a compact Calabi-Yau manifold, you're going to have a hard time. Well, at least you'll just get infinity, which is not very interesting. So in particular, even if you knew that there was a unique Calabi-Yau metric in every Bott-Chern class, the parameter space is still infinite dimensional, and you don't get a well-defined Hodge number. Well, I guess it's well-defined, but it's just infinity. So, so this shows that there are, if you want to do sort of mirror symmetry for Hodge numbers, you need to do some work. And so this is where this Kotsarkov-Kontsevich-Pantev proposal comes in. They gave a definition for Hodge numbers in terms of various data, logarithmic forms, weight filtrations, perverse sheaves, etc. And then Lentz and Przyjacielski computed these Hodge numbers for del Pezzos with del Pezzos and rational elliptic surfaces with an IK fiber, and found that both sides give the number of 10 minus k. Okay, so to answer some of these questions, I need to give a brief digression on what sections look like for this model fibration. So in general, a section of this model fibration is just this kind of multi-valued holomorphic function, where there are these, in order to be 2π periodic when you go around the singular fiber, you need these conditions, which just come from the fact that the image of sigma in C should be well-defined modulo the lattice. That's a straightforward calculation. So what you can do is you can relax these conditions. You can require just that these numbers are in, rather than being in Z, you can require that they're in Q or just R. And this gives rise to sections which are not well-defined, they're multi-valued. But if you take Q, then you get finitely many values, and if you take R, you get infinitely many valued sections. But the key point is that you can just check that it still makes sense. So if you use the Abel-Jacobi map with respect to these multi-valued sections, which you should really view as a map to the universal cover, you can still pull back the semi-flat metric, and it still glues to a well-defined metric. So there's a sort of extra symmetry hidden in the semi-flat metric, which allows you to make sense of the semi-flat metric with respect to multi-valued sections. So we'll call these non-standard semi-flat metrics, and they're quasi-regular in the case of Q and irregular in the case of R. So if you have a quasi-regular one, so you have a multi-finitely many valued section, then there's still a family of special Lagrangian bad cycles which fiber your space. But when you project them to the base of the fibration, they'll cover the circle in the base more than once, which is maybe not that surprising. And irregular semi-flat metrics cannot admit a special Lagrangian fibration because in fact there's no cycle that they pair to 0 with. So they're just topologically obstructed from admitting a special Lagrangian, even a Lagrangian. So the theorem is that if we start with a rational elliptic surface with an IK fiber and any Kähler metric on the complement of the IK fiber, then you can find a unique Calabi-Yau metric in the Bott-Chern cohomology class of your initial data, which converges exponentially fast to a multi-valued, so to a possibly non-standard semi-flat metric. So the key point here is, while the uniqueness is really important, but also the fact that this applies to all Kähler classes. So the existence part of this theorem, so once you have the right model, then Hein's work, he has a very sort of robust way for solving the Monge-Ampere equation, building on the work of Tian-Yau. So you can just kind of plug this into Hein's thesis, which is the machine that produces the Calabi-Yau metric. The uniqueness result is new. And it follows from a nearly optimal uniqueness theorem, which I'm going to talk about again below. And it shows that the parameter space for Calabi-Yau metrics asymptotic to semi-flat metrics is the cone of Kähler classes in the first Bott-Chern class, the 1-1 Bott-Chern cohomology. So that's still infinite dimensional, but at least we have now some sort of parameter space. Okay, and then as we'll see, well, I don't know if we'll get this far, but as we'll see later, these quasi-regular metrics are actually pretty important for mirror symmetry. So it's not just a cosmetic improvement. You kind of need them. Okay, so now we can answer this question of Yau, which says that if you start with a del Pezzo pair and a cycle in the elliptic curve, then you get this SYZ fibration, you hyper-Kähler rotate so that it becomes a holomorphic fibration. Then the symplectic form of the Ricci flat metric is one of these Calabi-Yau metrics asymptotic to a semi-flat metric. And it's essentially always non-standard. And in fact, generically, it's even irregular. So the only case where you get a standard semi-flat metric is when the torus has a rectangular domain, and the cycle you chose is one of the fundamental domains of that. Okay, so this is actually how we found these irregular guys in the first place, was just by hyperkähler rotating the Tian-Yau metric. Okay, so here's the sort of main application of this uniqueness result that I mentioned. So I'm not going to actually state the precise uniqueness result. I'm just going to talk about corollaries of it. But the real main application is the following. So if you have a rational elliptic surface with an IK fiber and two Calabi-Yau metrics with the same volume form, same de Rham cohomology class, and suppose they're both asymptotic at a polynomial rate to the same semi-flat metric at infinity, then they're the same up to a fiber preserving automorphism of the rational elliptic surface, or the complement of the rational elliptic surface, complement of the IK fiber, which is homotopic to the identity. So there's a sort of fiber preserving holomorphic map, a family of holomorphic maps, which will pull one of these Calabi-Yau metrics back to the other. So what that tells you is that if you quotient out the space of Calabi-Yau metrics asymptotic to semi-flat metrics by these by the connected component of the identity, and you can even put fiber preserving automorphisms here, then you get this well-defined Kähler moduli space, which is a non-empty cone with non-empty interior in the full de Rham cohomology. So you get something which looks pretty nice. It's just a sort of subset of R11 minus K with non-empty interior. So now we can start talking about Hodge numbers, because now we've sort of managed to quotient out and reduce to something finite dimensional.
You did say holomorphic, right? This F is a holomorphic.
Yeah, it's holomorphic. Yeah. It's I mean, you can imagine it's basically like a vector field along the fibers. Well, that becomes a little tricky to define at the singular fibers, but on the smooth fibers, that's what it is.
So can you say what happens to your infinitely many bot-Chern classes?
Right, so the bot-Chern classes, so that's some sense what's going on here is that the bot-Chern classes are generated by these automorphisms of the fiber. So if you have two metrics in the same de Rham cohomology class, then they might not be in the same bot-Chern class, but you can always pull back by a fiber preserving automorphism to make them lie in the same de Rham class. So in some sense, this bot-Chern cohomology is being generated by the action on the fibers of these fiber preserving maps. So
is it true that in your theorem, somehow what you're fixing is somehow just the geometric data of the semi-flat metric, but not a fixed semi-flat metric on Y?
Right, exactly, yeah. Yeah, so in some sense, all we're fixing here is the geometry at infinity and the de Rham classes. And even the geometry at infinity is pinned down essentially by the de Rham class. So there's not really, you don't really need to assume too much for this uniqueness theorem to apply.
Because lots of previous works like Collins and Hein would actually affix some kind of fixed asymptote on Y rather than fixing maybe just purely the geometry somehow.
Yeah, right. So I mean, right. So I mean, if you look at these semi-flat metrics, then you can kind of detect the de Rham class via the geometry of the semi-flat metrics, and then yeah, and that so right. So one of the steps in the proof of the uniqueness theorem is to show that you can solve the DD bar equation under these assumptions, so that they really do end up being in the same de Rham class. That's in some, and then with enough regularity. And then once you can solve the DD bar equation with enough regularity, then you can apply sort of Yau type uniqueness argument. Okay, so are there any other questions? If not, I'll continue. Okay, so So with this sort of discussion, so now we understand what these Calabi-Yau metrics look like on the rational elliptic surface. Now I can discuss special Lagrangian fibrations and SYZ mirror symmetry. So first theorem is that, so now we have these complete Calabi-Yau metrics with nice geometric properties. In fact, we know because of this hyperkähler rotation theorem that the geometry has to be exactly the same as the Tian-Yau metric. And we have a model special Lagrangian fibration at infinity. So then this sort of machine that I discussed at the beginning of the talk just runs in exactly the same way. So if you have a rational elliptic surface with an IK fiber and a Calabi-Yau metric asymptotic to a standard or quasi-regular semi-flat metric, then there's a special Lagrangian fibration with base being R2. And after hyperkähler rotating, it can again be compactified to another rational elliptic surface with an IK fiber. So essentially the same machine applies to prove these results. Yeah, so that's exactly the same machine. You have this model geometry and then everything sort of robust enough to carry over from the Del Pezzo setting to the rational elliptic surface setting. So now I can try to explain how to obtain SYZ mirror symmetry for these Del Pezzo surfaces. So we start with a pair, a Del Pezzo pair, Y with a smooth divisor D of degree K, and we fix a holomorphic volume form with a simple pole. And now you take the complement of D, and let's fix two classes in the elliptic curve, which are primitive and intersect maybe m times. You could take this to be 1 if you like, but I'll say where m comes in later. So let's identify, so we have this construction where if you have a closed curve in D, you can take its S1 bundle. So let's just identify alpha and beta with the classes of their S1 bundles in the cohomology space of the cohomology of the complement of D. And now we have to fix the normalization for omega. So we normalize omega so that the imaginary part of omega pairs to 0 with this class alpha. Okay, so these are the normalizations. In fact, there's more normalizations than this, but let's not worry about that too much. So now what we do is we take the special Lagrangian fibration of X associated to beta, not alpha. Okay, so we take this special Lagrangian fibration and you hyperkähler rotate and compactify it to a rational elliptic surface with an IK fiber. Okay, so now we've got some rational elliptic surface Y prime and a IK fiber D prime. So for K different than 8, there's a unique deformation family of rational elliptic surfaces with an IK fiber, just like there is for Del Pezzo surfaces, where for degree not equal to 8, there's a unique deformation family of Del Pezzo surfaces. And for K equals 8, there's 2 families, but they're distinguished topologically. So you can exactly match the P1 cross P1 family with a family of rational elliptic surfaces, and same for the first Hertzsprung surface. So now we can use the Torelli theorem of Grossack and Kiel, and there's to discover that there's this distinguished element in the deformation family of Y prime D prime, so we'll call it YEDE, which has trivial periods. And that's good for us because if you remember, the Tian-Yau metric is exact. So the periods, so to match periods, we should look for something trivial. So this pair was also used by Hacking and Keating in their recent study of homological mirror symmetry for log Calabi-Yau surfaces. So up to identifications, this class that we fixed at the beginning, because we chose, so if you just look at what the hyperkähler rotation gives you, this class alpha, it automatically induces a bad cycle in this YEDE, this convenient rational elliptic surface with an IK fiber that has trivial periods. And in general, it'll cover a loop on the base m, at least m, so m times. So where m is the intersection between alpha and beta, which is not hard to imagine since beta is now supposed to be the fibers of the special Lagrangian fibration. Okay, so now we can use this mirror map that was proposed by Gross in a paper from a while ago. And the mirror map's much more sophisticated than this, but at the very least, what it tells us is the right way to identify a Kähler class on the rational elliptic surface from the holomorphic structure is that the Kähler class omega check should be the imaginary part of omega, at least modulo scaling. So there's the full mirror map is more sophisticated and it maps the whole complexified Kähler moduli, but here's what it does on the level of Kähler forms, modulo scaling. And then modulo fiber preserving automorphisms by the uniqueness theorem, there's a unique Calabi-Yau metric on this rational elliptic surface in this Theorem cohomology class, which is asymptotic to a quasi-regular semi-flat metric. So we know it's quasi-regular because there is a bad cycle. Remember, because imaginary part of omega pairs with alpha to be 0. So there's automatically a bad cycle for this cohomology class. And by the theorem about existence of SYZ fibrations, this Calabi-Yau metric has an SYZ fibration with fibers in the class alpha. So then you can check by direct calculation that the SYZ fibrations of your del Pezzo surface and this rational elliptic surface that you've obtained are dual in the sense that they exchange the complex and symplectic affine structures on the base of the fibration R2. And modulo scaling, which I didn't say anything about, their volumes are inverse to each other. So if you scale everything properly, then the volumes of the fibers are inverted. So to compare with the work of Grossack and Kiel, so Grossack and Kiel produced this a tropical affine structure on R2 from a rational elliptic surface with an IK fiber. And we can show that the complex affine structure that we produce on the SYZ fibration of the rational elliptic surface is at least asymptotic to the tropical affine structure of GHK. So they're close. I mean, we don't know that they're exactly equal, but we can at least prove that they're asymptotic. So this follows again from this fact that we know that the Lagrangian mean curvature flow gives a sort of homotopy from the model fibration to the actual SYZ fibration near infinity. And then there's this calculation of Pascal that says that the Grossack and Kiel fibration agrees with the that the Grossack and Kiel affine structure agrees with the affine structure of the model fibration. So finally, let me talk about Hodge numbers. So since the Kähler classes always lie in a 10 minus k dimensional subspace pairing to 0 with some quasi bad cycles, the Kähler moduli is 10 minus k dimensional. So let me draw a picture of what the Kähler moduli looks like. So we have this 11 minus k dimensional space, which is H2. So this is R11 minus k. And now there's lots of Kähler forms which lie in this space, which do not have any special Lagrangian fibration. So having a special Lagrangian fibration means that you pair to 0 with some bad cycle, and that gives you countably many hyperplanes. So you get hyperplanes parametrized by Q. So we get Q hyperplanes. Which are each are 10 minus k, and each one of these is going to be the image of this mirror map. So the Kähler moduli will lie in each one of these, will lie in one of these hyperplanes given a choice of alpha and beta. So you have these many disjoint hyperplanes all intersecting, or at least open subsets of hyperplanes, which form the Kähler moduli. And so that tells you that the Kähler moduli is 10 minus k dimensional. And on the complex side, we also have a Torelli theorem of Nolan, which tells you that the deformation space of degree k del Pezzo pairs is 10 minus k dimensional. So you get this mirror symmetry for Hodge numbers, which are now sort of geometrically defined if we define the Kähler moduli in the appropriate way. And these also agree with the calculations of Luntz and Przylkowski for the KKP Hodge numbers. So there's a reasonably nice picture for SYZ mirror symmetry in the case of these non-compact Calabi-Yau surfaces. So going the other direction, so if we want to compare the complex moduli of rational elliptic surfaces with the symplectic moduli of del Pezzo surfaces, that seems that's a very interesting question. It seems harder because we don't know very much about complete Calabi-Yau metrics on del Pezzo surfaces, which, well, we know nothing about complete Calabi-Yau metrics on del Pezzo surfaces, which are not the Tian-Yau metrics. So in particular, if you wanted to have some non-trivial symplectic moduli of Calabi-Yau metrics, you need Calabi-Yau metrics which are not exact. So you need metrics which are necessarily different than the Tian-Yau metric. So I will end there. Thanks very much.
Thank you. Any questions?
I can ask one. So in this comparison with the Gross-Hecking-Kiel tropicalization, I just wanted to ask, are your singular fibers also just, is there just one singular fiber in your fibrations, or are they split up?
Oh, they'll be split up, yeah.
So what does it mean to be asymptotic?
So right, so that's a good question. I think what we mean is that there's, outside of a large open set, there's some diffeomorphism from R2 to R2, which maps affine coordinates to small deformations of the other affine coordinates.
It's outside of it.
Yeah.
Maybe I can ask one more. So
yes,
is there any hope to do something about the negative log Calabi-Yau surfaces, let's say?
Negative, so you mean when the
divisor doesn't support an ample divisor?
I see. So I see. So you mean like when the canonical bundle is ample?
Well, it's just it's not positive. It doesn't. The canonical.
I see.
Because
not ample.
There's also near sim like
right. So again, I think in that case, other than the rational elliptic, so the rational elliptic surface case would fit into that. But I think other than that case, we don't have any Calabi-Yau metrics as far, well, unless there's a fibration. If there's a fibration, then yes, then we can say like this Tian-Yau metric, this Tian-Yau theorem also produces Calabi-Yau metrics whenever you have a anti-canonical divisor that appears as a fiber of a fibration. So that's like what we did for the rational elliptic surface when you remove a smooth fiber. So in that case, we can probably do some part of this. But if it's not positive and not a fiber of a fibration, then I think we don't know anything about existence of Calabi-Yau metrics. So
those cases are supposed to be somehow, there is mirror symmetry, but I think there's a general expectation that it's somehow weaker. There's not necessarily a two-way mirror symmetry, maybe.
Just one way. I see.
Also, I read this in a couple of places too.
Yeah. Yeah, somehow we use so much of the geometry of these Calabi-Yau metrics that I think in a situation like that, you would need to first understand the existence of Calabi-Yau metrics, and then maybe from there you could go. But in general, I think producing these non-compact Calabi-Yau metrics is kind of hard because you have to have some idea of what the geometry is supposed to look like near the divisor.
What do you mean not a two-way mirror symmetry?
I mean, maybe I'm just well, this was, I think, written also in the ICM address of Kiel and Hacking.
I see.
It's somehow like, if you want
so like which side doesn't work?
Yeah, so I think you can take the imaginary part of the holomorphic symplectic form as the symplectic side, A side. And I think that has a nice kind of, at least algebraic, like not algebraic, but at least a non-Archimedean, but also possibly a complex mirror. But I don't know if something.
I see. Yeah, okay. Thanks. So, sorry to ask a question on top of the question.
Cross discussion is the best.
Other questions?
So maybe a very naive question. Can you maybe show your irregular semi-flat metric again? Because
yeah. It's just the same as the semi-flat metric, but what's changing is the identification of the actual fibration with the model fibration. So I didn't actually write the formula. So if you write it in terms of local coordinates that are like not defined just on the universal cover, but actually defined on the actual fibration, then it looks different. But I didn't write that in this slide. So, but I can show you that just.
Is it because there's no section or something?
Why it looks different? I mean, I think the so the right way to think of this. So we have this this fibration C mod Z plus K over 2 pi squared root of minus 1 log Z times Z. So the right way to think of this is to go to the universal cover, which is like C over like the upper half plane or something like that. And then here you can write down so Z is like e to the minus y or y is e to the minus z or something. Anyways, so up here you can write down the semi-flat metric in terms of the coordinates x and y. And then I think the right way to think of this is that, so you have this like disk. So if you have x over the disk, x mod over the disk, and then you have x over the disk. So if you have a section, you get a map. So if you have a genuine section, you get a map here, which is just this fiber-wise Abel-Jacobi map. So if you have a section, but if you have a multi-valued section, then you get a map only to the universal cover, the sort of fiber-wise universal cover. So this would be like a multi-section. So in some sense, when I write down when I define the irregular semi-flat metrics, I was cheating because I was not really writing them down on the model space. I was writing them down on the universal cover, but you can always write them down here as well, and then they'll look different because they're basically the semi-flat metric, the standard semi-flat metric, but when you translate by a multi-valued holomorphic section. So I didn't write that formula down, but I can certainly show you if you're interested.
So I vaguely remember in Gross and Wilson's original paper on K3, they also have a kind of Jacobian fibration situation and a slightly more general situation. So is that roughly the same issue?
Well, maybe. So I think usually, I mean, my impression from looking at, and maybe Mark can correct me if I'm wrong, but my impression from looking at Gross Wilson and also at Hein is that usually when people talk about these semi-flat metrics, they assume that the section is single valued. So I think that's the case in Gross Wilson, and it's certainly the case in Hein. But the observation is just that that if you have a multi-valued section, then these metrics still make sense and glue together to something well-defined. And you can show that this kind of behavior that I wrote down before, like you could of course consider multi-valued sections to the universal cover, which are more exotic than the ones that I wrote down. But you can show that those are the only ones for which the semi-flat metric pulls back to one that's well-defined.
So is it because, I mean, somehow, when you're taking a multi-valued section, I guess you're choosing one particular value at one time. So are you roughly saying that choosing different values would give you the same metric after all? So you don't have to worry about it. Is that...
Right, yeah, that's somehow the multi-valuedness, the sort of, the change, that if you go around, then you get a different value. So the translation between those two values is an isometry of the semi-flat metric. So basically, you have an extra group invariance that allows you to show that the metric still glues together to something well-defined.
I mean, you should have an S1 in action, S1 invariance there. So you have quite a lot of flexibility.
Right, exactly, yeah. Yeah, so basically, I mean, what you can do, it's a simple calculation. You just go to this semi-flat, this formula for the semi-flat metric, which is, making myself dizzy. Okay, which is here. And now you consider, you consider pulling this back by a multi-valued holomorphic map. So x goes to x plus sigma of z. And then you just check under what conditions does that glue again when you go, does that glue to something well-defined when you go back around the circle? So that gives you a differential equation, which basically you have a differential equation that equals something, and that something on the right-hand side needs to be 2 pi periodic. And you can just check that the only solutions to that differential equation are ones that look like holomorphic function plus log z squared. And there are no other solutions.
Other questions? Well, we can thank Tristan again, and you can discuss and socialize more at Gather Town, or keep talking here. I'm going to stop the recording now.